Hi, everyone. My name is Ira Pramanik. I'm the program manager for Christine and Sneha. Sneha is the mentor, and she is actually right now on a flight to the West Coast for a conference that she's going to participate in. I'm going to read her intro for her on her behalf for Sneha, no, for Christine. My name is Sneha, and this term I mentored Christine Johansson. She is a 10th grader at the Dominican Academy in New York. Christine is such a grounded and intelligent person. It was my pleasure to mentor her. She excels both academically and in sports such as tennis and running, and we bonded over our shared love of musicals and TV shows. Christine has a personal connection to Alzheimer's disease and is passionate about using coding and biomedical engineering for early disease prediction. She has done coding courses in Python already, and it was a pleasure to build on this with her and help her develop her own neural network for Alzheimer's detection. I'll let Christine share her project with you.
Thank you. So like I said, I'm Christine Johansson, a 10th grader at Dominican Academy. Next slide, please. So my mentor is Sneha. She's a PhD candidate at Columbia University studying biomedical engineering with a focus for AI for medical imaging. So she's from England and enjoys yoga, cooking, and musicals. And she lives in New York, so we were actually able to meet up soon, as you can see in the image. Next slide, please. So the goal of my project was to build and evaluate the accuracies of models trained on different data. So we used the data from the OASIS dataset, and we focused on the clinical and demographic data, as well as 2D MRI slices. And this entails the skills of pre-processing, deep and machine learning, and Python using PyTorch. Next slide, please. So I chose to focus on Alzheimer's disease because it runs in my family, and I think that disease mechanisms are really fascinating. And I also specifically chose to do deep learning because it has the potential to transform industries, including medicine, which is something that I'm really passionate about. I also love how coding exercises logical thinking and can be used to interpret data. And I wanted to learn how computers can see features and images of the brain. Next slide, please. So the highlights of being a Magic Mentee have been understanding the real-world applications of deep learning for biomedical imaging. I also learned about Alzheimer's disease pathobiology and receiving the invaluable guidance from my mentor, Sneha. I've learned how to analyze and summarize university-level research papers, which is something that I had not previously done, and present the information in a simplified and engaging, understandable way. The challenges of this have been learning a variety of new terms in such a short time, such as pooling and normalizing, and navigating complex topics like the math behind convolutional neural networks and the processes of neuroimaging machines like PET and MRI. Next slide, please. So far we've completed a literature review and learned a lot of background information on deep learning for biomedical imaging. And I coded my own classification model for Alzheimer's disease detection from handcrafted features extracted from brain MRIs. And I'm in the process of analyzing the 2D slices from brain MRI and coding a convolutional neural network to detect Alzheimer's in these. Next slide, please. So Alzheimer's disease is an extremely prevalent neurodegenerative condition and is the leading cause of dementia. So it affects millions of people worldwide, and that number is only increasing. Symptoms can include memory loss and reduced mental capacity. And as we can see in the diagram, it is caused by when an enzyme abnormally cleaves these APP proteins to produce senile plaques, which can disrupt neural communication. Next slide, please. So MRIs can be an extremely helpful tool for detecting Alzheimer's. So as you can see in the image, a brain with Alzheimer's disease may present with brain atrophy, particularly in the ventricles and cerebral cortex. But when it's not as obvious, like in this image, it can be really difficult and expensive for doctors to find Alzheimer's disease in these images, which led many scientists to look to deep learning for detecting Alzheimer's. Next slide, please. So we found in our literature review that there are two main approaches for using deep and machine learning for Alzheimer's detection. So both pre-process the brain MRIs using FreeSurfer, but one method is using the handcrafted features such as the volume of the hippocampus and implementing a fully connected neural network. But another method is to use a convolutional neural network and operate directly on the 2D and 3D MRI. And I also have a literature review in the appendix, which you can ask me about after, but it won't be included in this presentation for the sake of time. Next slide, please. So we use the OASIS dataset and mainly focused on the tabular dataset, so that is the clinical and demographic information, and it includes the image-based features, demographic information, and Alzheimer's status, so demented, non-demented, and things like that. Next slide, please. So to do the data analysis, we first did pre-processing in Python. So for the continuous features, we scaled this to a normal distribution, as you can see in this diagram of the example age. And then for the categorical features, we used min-max scaling to -1 and 1. And for the Alzheimer's disease status, we converted this to a binary task where demented equals 1 and non-demented equals 0. Next slide, please. So first we used logistic regression. So we had to split the data into training and testing sets, and we applied this baseline linear model of logistic regression, which it's basically a classification model, and it produces probabilities. And through this method, we were able to achieve an accuracy of 95.77% in detecting Alzheimer's versus non-demented. Next slide, please. And then we built a neural network to try to test if it could reach a higher accuracy than just logistic regression. So this was built using PyTorch, and for each batch, we used cross-entropy loss to essentially calculate how wrong the model was. And based on this calculated loss, we computed gradients, which are the derivatives of the loss function, which we use this information to then update the weights. And in the image, you can see that we've defined the neural network and split it into the batches and defined the loss function. Next slide, please. So this is my demo. Hopefully the audio works. Data analysis. So here we define the neural network, and the way we've set it up allows us to change the input size and hidden size. And ReLU here adds nonlinearity. So this is an example of the architecture of the neural network. So here we have our training of the neural network, and the way we set it up allows us to change our decay values, batch values, training epochs, and hidden sizes in a grid search. So when we run this cell, we can see the training loss as we've trained the model. And we can also see that we previously ran a grid search and found that our highest accuracy was attained using 250 epochs, 8 hidden sizes, a low weight decay, a batch size of 5. And these allowed us to reach 100% accuracy. Next slide, please. Okay, so for the image data analysis on the 2D MRI slices, these were the same participants as in the tabular that we just looked at. So as you can see in the top image, there were about 150 to 300 slices per person, which is a lot of data that can lead to overfitting or just a really long processing time. So we used entropy to select only the top 10 slices that had the most entropy or the most information that we have of them. So next slide, please. So to pre-process the image, we were able to perform simple transforms. So as you can see in the first 2 images, we've changed the sample original image to be resized with and without smoothing, so you can see how that affects the image. And we performed image cropping, so that is only the top left corner in the top right. We also performed complex transforms, so the Sobel edge detection looks at the horizontal and vertical edges, and blob detection, which, as the name suggests, it looks for blobs within a specific size range that we set, and both use handcrafted filters. Next slide, please. We also implemented intensity transforms, which increase or decrease image contrast. So this red line in the graph is the cumulative fraction So it shows the percent of pixels that are less than or equal to given intensity values. And then the gamma corrected, which is this middle row, we had gamma equals 2, which means that it reduces the contrast between bright and dark tissues. So here, the circled bit, you can see that since we reduced the contrast, it would be more concentrated towards a lower pixel intensity. And you can see that that made the image darker. And logarithmic corrected does the opposite. So it increases the contrast between the bright and dark tissues. It makes the very dark pixels brighter, which again, you can see in the image. And since it does increase the contrast, you can see that the range of pixel intensities is much larger than that of the gamma. Next slide, please. So future work is to actually finish coding the 2D convolutional neural network based model. So as you can see, I've made some progress in this. The first screenshot defines the convolutional neural network, and the next one implements a custom image data set. Next slide, please. And that is all. Thank you. And a special thank you to Magic and my mentor, Sneha.
Amazing job. What questions do we have virtually for Christine?
Hi, this is Ira. Christine, I have a question for you. So, I mean, I think I got that you gathered all the data from some public repository to train the model on, right?
Yes, correct.
And then have you actually, I know this is hard. First of all, congratulations, 10th grader doing this, just mind-boggling. But were you able to actually run it on, so you did the testing on part of the data. Have you actually shared this work with anyone? I'm wondering if we, some prelim results maybe, and that's like ambitious, but worth trying.
Yeah, so I haven't been able to look into like sharing my results with a larger audience yet, but I hope to, especially as I finish the 2D convolutional neural network in the summer.
Congrats, great job.
Thank you so much.
Thank you. Great job.
I have a question. Can I? Do we have time for one?
Yeah, absolutely. Come back up. One more question. Absolutely.
Congratulations on your project. That's so much information. That's incredible. Like it's a lot. So just out of curiosity, because it's not easy to understand everything that you shared, really. How much of your mentoring time did you spend on learning about this new concept and thinking in before you started coding and using data?
Yeah, so we did spend a significant amount of time learning the concepts since it was really complicated. But my previous experiences with deep learning, especially through Girls Who Code, was definitely a help in that. And Sneha was able to offer me many resources in learning more about this, which sped up the process. But yeah, we did spend a significant amount of time studying that before trying to do any like fancy neural networks.
Yeah, awesome. Congrats.
Yes,
Thank you.
Congratulations. Really, congratulations.